third video in the series now of talking about forces. So now we're last video was the one where we looked at everything in equilibrium. And remember, when we're in equilibrium, we either have no motion or constant velocity. Now we're looking at things in terms of equilibrium, and not in equilibrium, excuse me. Anytime that we're not in equilibrium, we have acceleration. And again, what this means is that when we look at our forces, okay, excuse me, I forgot to get my colors going. Here we go. When we look at our forces, we now have uneven forces. So in other words, our forces say that we will have a net force that will be equal to something, and that means that it's equal to a mass times an acceleration. And so the net force is equal to that, or proportional now to that acceleration. So in other words, our object is now speeding up. It's changing its speed. All right, so now the first situation I want to look at is just with a box on an incline, okay? And so you may remember that we did our free body diagram in the last video for our box on the incline, where we have F of G, and we have, say, a frictional force, so an F of F, and then we have a normal force. And the normal force would be looking like this. And then we say, well, what really happens now is that gravitational force needs to be split up into its components. So I'm going to go into my component color. So I'm going to say that I have F parallel versus F perpendicular. And again, I look at this from my relationship standpoint. I may be in equilibrium. It's not like my box is going to jump up or go down, okay? So in other words, I have an equilibrium situation between those two. But I might be out of equilibrium. So let's just say I got to redraw my arrow here. Let's say that we have just a very small amount of friction force. So in other words, the arrow here is greater than the arrow here. That means that we have net force, okay? So when we set up an equation now to look at this, we're going to say that F net, okay, a net force, is equal to, now we look at this and look at our arrows, our force parallel minus my force of friction. That's how we build these relationships. So again, our net force is equal to this. Now a net force just means that we have a mass times an acceleration is equal to that force parallel minus that force of friction. And remember that the force parallel is nothing more than a component based on an angle. Okay? And so that's kind of our big physics principle here. Now we may again run into a situation where we get two unknowns in this problem, and if we have two unknowns, we have to have two equations. Our second equation could come from our force normal being equal to my force perpendicular. Okay, and that's an equilibrium situation, because again, we're not moving up or down on that. So again, when we try to think about these, we think in terms of a free body diagram first. We want to split up and look at our vectors to make sure, our force vectors, to make sure that we have components that lie on XY planes. We try to look at how we separate our x's from our y's, and then we're looking now as a key for those net forces. So where is one arrow bigger than the other? Okay. Now that brings me to my next problem, and this is the one that's going to be hanging up in the room. So it's called an Atwood's machine. In other words, it's just two masses hung over a pulley. But this tension, now again, because this is one single rope, this tension through this rope is going to be the same tension through it. Again, we're looking at it and we're saying that we have acceleration. This is similar to what we did in our lab. So again, here was the pulley that we had, and here's my block, and it was connected to the string, and we had a mass hanging down here. This is another variation of an Atwood's machine. So again, I have now free body diagrams that I'm going to write for both of these. Okay. So again, how we think about this, we think about this in terms of free body diagrams. Okay. So now the mass 1 here, okay, that mass has an F of G going down, okay, and it has an F of T going up. So it has a tensional force going up. Now in this case, the downward arrow is bigger than the upward arrow. So I have net force going down. So in other words, again, if I think in terms of my net force, Okay, I have a net force that's going down. So I have some arrow that's going to go down there, which means that I'm going to see acceleration downward. I can build a relationship from this. So my F net is equal to my Fg minus my Ft. My F net is nothing more than the mass times an acceleration. So in other words, if I'm looking for the acceleration of my object, that's something that I'd be able to find. Fg would be the weight of that, or the mass times gravity, and the Ft might be my unknown. So again, I may have a situation where I have an equation that comes up with two unknowns. Now I do this usually for both of my masses. So if I go over here, I might have a smaller mass now, an Fg over here, and I have that tensional force, okay, that force of tension, and this arrow here and this arrow here are the same sized arrows because they're the same tension, okay? The tension has to be the same. The other thing that happens then is that we can then create this other equation where we have a F net is equal to F of T now minus F of G. So in other words, my tension force is greater than my F of G. So if I wanted to follow along with another arrow, I'd have a little net arrow that would be going up. Again, when I look at this, I look at it in terms of the mass of the object times an acceleration is equal to that Ft minus Fg. And keep in mind now that this is the mass of 1 and this is the mass of 2. They're two different masses, but the accelerations are the same. Okay, so this thing is going to change its speed as fast as this thing is changing its speed. Okay, and so that's kind of how we look at this. And if we look at our number one problem, and we'll probably talk about this one, maybe we've already talked about this one in class, but I have a free body diagram going down, I have a tension going up, okay, and I know that this arrow here is going to be greater, so Fg is going to be greater than Ft because the object drops. So we see motion going this way. Now, in this particular situation, when we were doing it in lab, we looked at this and we said that it's going to be frictionless. Okay, and when we say it's frictionless, so it's essentially if I do my free body diagram, I have a force normal, I have a tension force, okay, and there's no other force, oh, and I have a weight, Fg. My Fg and my Fn are equal to each other. The cart didn't go up and the cart didn't go down. The cart just went to this way. So in other words, my net force becomes that tensional force. So my F net is equal to that F of T. Okay. Again, these are going to be probably the hardest kind of concepts to go over, and you may want to kind of go back and pause as you're watching this video and maybe watch it a second time. I don't have any more to this one tonight, so again, I want to leave it, with a chance for you to maybe watch this one twice to really kind of let it sink in and go over it. And I would suggest maybe going to some of the extra websites on this particular topic. So again, we'll work on some more of these problems come tomorrow and kind of complete our lab reports and things like that, or lab activity. And remember, watch it twice, think carefully, and happy physics.